artificial transmutation of elements. Lighter elements like carbon, nitrogen, phosphorus can be transformed into other elements. Such a transformation is known as artificial transmutation of elements. To understand this and to study this, let us study the Rutherford's experiment. The experimental setup consists of a thick glass tube. It has a side tube for evacuation and for introducing the required gas into this tube. Radium C is placed at the end of an adjustable rod which is placed from left side. And on the right side there is a thin silver foil which acts as a window, and beyond that thin silver foil a fluorescent screen is placed. Beyond the fluorescent screen a microscope is placed to observe the scintillations on the fluorescent screen. So the apparatus consists of thick glass tube with a side tube for evacuation and for introducing the required gas, and the radium C is placed at the end of an adjustable rod from which alpha particles are emitted, and they will pass through the thin silver foil and they fall on the fluorescent screen, and the scintillations will be produced. They will be observed with microscopy. Discovery of proton. Proton was discovered during artificial transmutation. Just now we have seen an experimental setup for artificial transmutation. Here scintillations are observed on the fluorescent screen. These scintillations can be observed even if the microscope is moved away some 40 centimeters from the source. But actually alpha particles can travel only up to a maximum distance of 8 centimeters in air. Alpha particles can travel only 8 centimeters in air. If the scintillations are observed, even if the screen is moved away 40 centimeters from the source, that means these scintillations are produced not because of alpha particles but by some other particles. The scintillations should be produced by particles other than alpha particles. By conducting experiments, it is learned that the mass of this particle is equal to that of hydrogen. The mass of this particle is equal to that of hydrogen atom, and this particle carried a positive charge. The magnitude of this positive charge is found to be equal to that of the electron. This particle was not known at that time, so it was named as proton. Suppose by introducing nitrogen gas into the Rutherford's apparatus, if these scintillations are observed, then Rutherford concluded that the nitrogen nucleus is hit by alpha particle. On being collided by alpha particle, disintegrates into oxygen nucleus and a proton. The nuclear reaction can be represented as follows: nitrogen 714 plus helium 24 gives rise to oxygen 817 plus proton 1H1. This is how we can represent the nuclear reaction. Here the transformation is that of nitrogen into oxygen. Nitrogen nucleus is transformed into oxygen nucleus, and a proton is released due to the collision of nitrogen with alpha particle. So this is artificial transmutation. During this process, radioisotopes. Before we go into the name, first let us understand artificial transmutation. The process of transforming stable nucleus of one element into a stable nucleus of another element is called artificial transmutation. In artificial transmutation, we go from one stable nucleus to another stable nucleus. Artificial transmutation is possible for lighter elements up to the mass number 20. Artificial transmutation is possible for lighter elements, say up to the mass 20. In some cases, it was noticed that the newly formed nuclei exhibited radioactivity. The newly formed nuclei exhibited radioactivity. One such example is radiophosphorus. The radioactivity exhibited by radiophosphorus. The nuclear reaction for radiophosphorus can be written as aluminium 1327 plus alpha particle He24 gives rise to phosphorus 1530 plus neutron N01. Here phosphorus 1530, it is an isotope of phosphorus. It is radioactive. Its half-life period is only 3.25 minutes. So after 3.25 minutes, it gets disintegrated into silicon and positron. So this lives only for a short time, 3.25 minutes. Thereafter, it gets disintegrated. So the disintegration reaction can be written as phosphorus 1530 gives rise to silicon 1430 plus positron E plus 10. Such elements, newly formed elements like phosphorus, are termed as radioisotopes. The elements which are produced due to artificial transmutation and which exhibit radioactive phenomena are radioisotopes. They are not naturally available. They are produced artificially in nuclear reactors. Discovery of neutron. Discovery of neutron. The nuclear reaction that led to the discovery of neutron is the transmutation of beryllium into carbon. The transmutation of beryllium into carbon led to the discovery of neutron. In this reaction, uncharged radiation was discovered and was thought of to be gamma radiation. Initially, this was thought to be gamma radiation, but later on it was decided that is neutron. The original reaction can be identified as beryllium-49 plus alpha particle 24 He24. It combines to become carbon 613, but it decays as carbon 612 plus gamma radiation. This is the original reaction, original thought of reaction, not reaction. Here gamma radiation is an uncharged radiation, uncharged particle. This highly energetic radiation. From the experiments of absorption of these radiations, from the experiments of absorption of gamma radiation by lead, it was learned that they should have an energy around 7 million electron volts. 7 MeV should be the energy of this gamma radiation. From absorption experiments, the energy of this radiation was determined to be 7 MeV. When this radiation is used in the transmutation experiments once again, they were found to eject speed protons. When this gamma radiation, it was when this radiation, which is thought of to be gamma radiation, actually it is not. When this radiation is used in the transmutation of experiments, in the transmutation experiments. Protons were released. High-speed protons with a maximum energy of 7.5 MeV were released. High-speed protons with an energy 7.5 MeV were released by bombarding radiation with this gamma radiation, supposed to be gamma radiation. And these experiments were conducted from hydrogenous substances like paraffin, wax, water, paper, etc. So when this, from absorption experiments, the energy of this radiation should be 7 MeV, but from hydrogenous substances, from collision with hydrogenous substances, the energy is estimated to be 64 MeV, and in some other experiments the energy was something different. Chadwick observed this discrepancy in the energy of this radiation. But by treating this energetic radiation as a chargeless particle, he could solve the discrepancy of the energy of this radiation. So he identified them to be neutrons. Now let us pass on to the study of Chadwick's experiment. Chadwick's experimental setup. It consists of vacuum chamber. Inside the vacuum chamber, at the left, a source of alpha particles, here polonium, is placed. It is named as S. In front of this source, a slit is placed to obtain a beam of alpha particles. This alpha particles beam, it will be incident on beryllium, a block of beryllium, and thereafter neutrons will be emitted. They will pass through a small window and they will fall on a paraffin block. In the path of neutrons, a block of paraffin is placed. The neutrons in turn produce protons from paraffin block. These protons are collected by the ionization chamber, which is connected to an electrometer which measures the ionization current. Source of alpha particles is polonium, and these alpha particles, they travel through beryllium. They will be incident on beryllium. Due to the nuclear reaction of the alpha particles with beryllium, neutrons will be produced. Neutrons, they bombard the paraffin block and thereby protons will be ejected. These protons will be collected by the ionization chamber and the ionization current will be measured by an electrometer. This is the experimental setup of Chadwick. The energy of the neutrons is measured, is calculated, is estimated from the energy of the protons. And from this experiment, Chadwick concluded that the particles emitted from beryllium after the interaction of the alpha particles with beryllium are found to be non-charged particles, uncharged particles, and he identified them to be neutrons. Neutron and its properties. Chadwick identified the particle as neutron from his experiments, as we have seen just now. The nuclear reaction in the production of neutron is identified as beryllium Be49 plus alpha particle He24 gives rise to carbon 612 plus neutron N01 plus Q energy. This is the reaction which is identified by Chadwick. Neutron is an uncharged particle. It has got very high penetrating power and very low ionizing power. It is uncharged, high penetrating power and low ionizing power. Inside the nucleus, it is a stable particle. As long as it is inside the nucleus, it is stable, but outside the nucleus, it is unstable. Neutron is unstable when it is outside the nucleus. Its half-life period is 1000 seconds. its half-life period is 1000 seconds. It decays into proton, electron and antineutrino. Neutron decays into proton, electron and antineutrino. It can be represented by the following nuclear reaction. N01 neutron, it gets disintegrated into proton 1H1 plus electron E-10 plus antineutrino nu bar. Slow neutrons are useful in the disintegration of uranium atom. Slow neutrons are useful in the disintegration of uranium atom, in the fission of uranium. Fast neutrons become slow neutrons on passing through materials like paraffin wax, heavy water or graphite, known as moderators. Slow neutrons are also called as thermal neutrons. Thermal neutrons. Their energy will be less than 1 electron volt. Nuclear fission. Nuclear fission. When uranium-235 is bombarded with slow neutrons, it splits up into two fragments of nearly equal mass. When uranium-235 is bombarded with a slow neutron, it splits up into two fragments of nearly equal mass, and 3 neutrons will be emitted along with 200 MeV of energy. Two equal fragments, 3 neutrons and 200 MeV energy. The reaction can be written as U92-235, uranium-92-235 plus neutron N01 gives rise to barium Ba 56-141 plus krypton 3692 plus 2 neutrons, 2 into N01 plus 200 MeV. Sometimes 2 neutrons are emitted, sometimes 3 neutrons are emitted. In general, the process of breaking up of nucleus into 2 or more equal fragments is called fission. In general, the process of breaking up of a nucleus into 2 or more equal fragments is called as fission. We imagine that uranium nucleus is spherical in shape. Uranium nucleus is supposed to be spherical model. Then when it absorbs a neutron, then it gets excited, and thereby it deforms into oval shape. From spherical shape, it deforms and takes the shape of an oval. This is the excited nucleus. Slowly this excited nucleus gets deformed into dumbbell shape. From oval shape, it slowly deforms into dumbbell shape, and thereafter it will break into two fragments, barium and krypton. Along with 3 neutrons are emitted. This is the rough process of breaking up of the nucleus. Explanation of fission process. Now let us explain how the fission process takes place. The nucleus is considered to be in the spherical shape because of surface tension forces of the nucleus. Because of surface tension forces, the nucleus will be of spherical in shape. When a neutron is absorbed by the nucleus, excitation energy is imparted to the nucleus. Excitation energy is imparted to the nucleus when it absorbs a neutron. The excitation energy tries to deform the nucleus, whereas the surface tension force tries to keep the nucleus in its spherical form. Surface tension force tries to keep the spherical form, whereas excitation energy tries to deform the nucleus. As a result, oscillations are set inside the nucleus. Due to the oscillations, the nucleus is deformed and attains the elliptical shape and then breaks into fragments and neutrons. If the excited energy is sufficiently large, the ellipsoidal nucleus attains the dumbbell shape. Ellipsoidal nucleus attains the dumbbell shape if the energy is sufficiently large. The attractive forces become less. The attractive force becomes less as the surface area increases. As the surface area increases, the cohesive force decreases. The electrostatic repulsive force dominates and the nucleus breaks up. As the surface area increases, the attractive force becomes less and thereby the electrostatic force, repulsive force dominates and the nucleus splits up into fragments. Chain reaction. Chain reaction. The reaction that is sustained by the neutrons produced in the fission process is known as chain reaction. If you take a large number of uranium atoms, by sending one neutron, the entire uranium can be disintegrated. One neutron undergoes collision with one uranium atom and breaks it up and produces 3 neutrons. One neutron produces 3 neutrons by disintegrating one uranium atom. These 3 neutrons, they collide with 3 atoms, each one collides with one atom and each one produces 3 neutrons. So 3 neutrons they produce 9 neutrons by disintegrating 3 atoms. The 9 neutrons produced, in turn, they collide with 9 uranium atoms and by disintegrating them, they produce 27 neutrons. Like this, the number of neutrons produced, they multiply in geometrical progression. Their number will increase in geometrical progression and they will sustain the disintegration process without the help of neutrons from outside. Such a process is known as chain reaction.